We will now look at the solution to question 4 and question 6 of the tutorial on tangents and normals. In question 4, we are given the equation of a curve C with a constant k. First, we need to find dy dx in terms of x and y. In this question, we will simply differentiate the equation A is given. Do not attempt to make y the subject in this equation. Using implicit differentiation, going through step by step, differentiating x cubed will give us 3x squared. Differentiate x, y using product rule, we can keep x, and differentiate y to get dy dx. And plus, keeping y, differentiate x will give us y. Differentiating to y cubed, they will leave us with 6y dy dx. And on the right hand side, differentiating the constant k will give us 0. Grouping the terms together, we can simplify dy dx as shown on the screen. In the next part, we are told that it is given that C has a tangent which is parallel to the y-axis. We need to show that the y-coordinates of the points of contact of these tangents with C must satisfy the equation as given. So we are looking at tangents that are parallel to the y-axis. That simply means that dy dx at those points is undefined. Looking at our dy dx from the previous part, this simply means that the denominator of dy dx must be equal to 0. Solving the denominator to be equal to 0, we get x equals to negative 6y squared. Do note that this is not the equation of the tangents. So what is this? This is the relationship between the x and y coordinates of the points on the curve where the tangent is parallel to the y-axis. So, in order to find the coordinates of the points on the curve, we substitute this back into the equation of the curve C. Doing so, simplifying, we will reach what we need to show. Moving on to the next part, we need to show that the constant k is less than or equals to 1/54. Again, we look at what we have just shown. Now, if we let big y be y cubed, we can simplify this equation into one that is a quadratic. Hence, in other words, if there are to be real solutions of y, which means there are solutions to the equation above, all we need is for the discriminant to be more than or equals to 0. Starting from this, we eventually be able to reach what we need to show. Moving on to the last part of this question, we need to find the possible values of k in the case where the line x equals to negative 6 is a tangent to C. First, due to the x equals to negative 6 is in fact parallel to the y-axis, so this last part follows on from the whole question. When the line x equals to negative 6 is a tangent to C, making use of what we have done so far, if we equate this to negative 6y squared, this will give us y to be equals to plus or minus 1. In other words, the coordinates negative 6, 1 and negative 6, negative 1 are points on the curve C where the tangent is parallel to the y-axis. Looking back at the equation that we have solved, that we have shown earlier on, putting the values of y into this equation, they will give us the two values of k as we need for this question. Moving on to question 6. In this question, we are given a curve that is defined by a pair of parametric equations. First, we need to show that dy dx equals to negative tangent theta. Using the pair of parametric equations, with the x equation, first we find dx d theta, and from the y equation, we find dy d theta. And as we have known from the notes, dy dx will be dy d theta divided by dx d theta. Simplifying that, we can simply show that dy dx equals to negative tangent theta. For the second part, we have a tangent to the curve at a point with parameter theta that cuts the axis at s and t. We need to write down the equation of the tangent and show that the distance st is independent of theta. First, for the equation of this tangent, using y minus y1 equals to m times x minus x1. This is the equation of our tangent. Looking at the diagram on the right hand side, imagine the line is the tangent of our curve at the point with parameter theta. Now, let's say the y-intercept of this tangent is the point T. How do we find the coordinates of this point? We simply sub x equals to 0 into the equation of the tangent. Solving this, it gives us y as a sine theta. This is the y coordinates of the point T and also the length of OT. Similarly, let's say the x-intercept of the tangent is the point S. In order to find the x coordinate of this point, we let y equals to 0 in the equation of the tangent. Solving for x, we will get x equals to a cosine theta. This is also the length of OS. Now, if we are looking for the distance ST, using Pythagoras' theorem, we can find ST using square root of a sine theta square plus a cosine theta square. Simplifying this, we get square root a square, which will give us modulus a, but since a is known to be a positive constant, hence our ST is just simply equals to a, and we have shown that it is independent of theta.